bonds and bonding energy. And as you look at the picture right here, you can see that there's a bit of a menu, part of the menu from several different fast food restaurants, and you can see that calories are prominently displayed right here. 540 calories for a Big Mac at McDonald's. Taco Bell offers the beef gordita supreme for only 310 calories. Well, let's take a look at where those numbers come from and what those numbers mean. So the concepts that we'll be looking at, the objectives for today are why do atoms bond? And we'll look at bond length, long bonds between atoms or short bonds. We'll look at the energy. This is going to be a big part of it. We'll look at the energy given off or absorbed when chemicals bond. And last but not least, we'll take a good look at calorimetry, which is a method of figuring out these numbers right here. Look at that, 140 calories per dollar. What a great deal. Okay, here we go. So, formation of covalent bonds and energy. I'll show you this video up here in class. But for right now, let's just review the first topic about bond energy, and that's this. Bonds form to lower the energy of a system. And so the system means all the chemicals that are involved in the chemical reaction. But it also means a little bit more than that. It means the surroundings as well. Are the surroundings giving energy to a reaction, or are the surroundings absorbing energy? So bonds form to lower the energy of a system. That's why they form, because everything in the world likes to have low energy. It's a fundamental law of physics and chemistry. Number two, attraction and repulsion cancel out to form a covalent bond at a length where the potential energy, the PE, potential energy, is at a minimum. And that is, we're looking at this right here. So here you see two atoms, one atom, two atoms. Here you see the same two atoms, here the same two atoms, and over here two atoms. Way over here, the atoms are not bonded to one another. They're too far apart. And so over here, you can see the two atoms are snuggled up together really, really closely. Well, neither of those is an ideal situation, and they have high energy. So energy is on this axis right here, high energy. But there comes a point at which the atoms are just the right distance apart. Okay, so that's right down here, where the two atoms are just the right distance apart, where the bond energy is the lowest, and so that's where they sort of establish the bond length, the distance between the two atoms. So here's the two nuclei I put in there, so that would be like the bond length. In this case, they say 75 pm, and that means picometers. And picometers is 1 times 10 to the negative 12th meter, so a very short distance, but that's the ideal distance. It's kind of like the three bears. You don't want them to be too close. You don't want them to be too far apart. You want them to be just right. And so there's a whole bunch of forces that are at work. The electrons and the protons attracting one another. But if you get the two atoms too close together, like here, then remember the nuclei are positively charged. So those two nuclei start saying like, no, I don't really like you. I don't like you either, because they're both positively charged. So they're too close together here. And then up here, they're getting so far apart where the protons and the electrons don't really have an attraction for one another. So down here is just the right distance. And so this is called the bond length. Number three, bonds have a particular amount of energy. See table, that'd be this one right here. So for example, a hydrogen-hydrogen bond has this much energy, 440. Now we should really look at the units involved, and it's kilojoules per mole. Now you've seen joules and kilojoules before when we talked about energy previously this year in regard to wavelengths. You might recall that we saw, a wave would be like this, and we calculated a lambda, a distance, and a frequency, and we calculated the energy. And energy was given in joules of energy. Here we're talking kilojoules, which is 1,000 joules, and also it's per mole. And we should probably take a quick rundown memory lane there in that regard as well. And moles are a chemist's counting number, and the number is 6.02, sorry about that, times 10 to the 23rd particles. So in this case, if you broke that bond, if you broke 6.02 times 10 to the 23rd of those bonds, it would require 440 kilojoules of energy. So 1 mole of those bonds being broken would require this much energy. Okay, and oxygen-oxygen double bonds. To break that bond right there, that bond is worth 500 kilojoules per mole, and OH bonds are worth 460 kilojoules per mole. And we can predict the amount of energy released or needed for a reaction using this equation, which you should probably write down. And the terms are delta E. So delta means change in energy before and after. The change in energy is equal to the energy of the bonds broken minus the energy of the bonds formed. So this is bond energy over here. Let's take a look at this example. 2 hydrogen molecules plus 1 oxygen molecule makes 2 H2Os. Over here is what you start with. These things are already bonded together. The H2s are like this up here. The O2s are like this over here. And then we're going to break those bonds and we're going to make 2 H2Os. And so we're going to take the bonds broken and subtract the amount of energy found in the bonds which are formed. All right, 2 H2s. So there's an H, bam, break it. Bam, break it right there. So 2 of those. Now it's actually 2 moles of these. And each mole, these are H's, that's a hydrogen atom, that's a hydrogen atom. So this is each H bond, that's worth how much? There it is, 440. So there's 440, 440 kilojoules per mole there, 440 kilojoules there. Together that's 880, I think, isn't it? 8. I wish I could write better with this thing. Okay, and now here, this is an oxygen molecule, so this is actually a double bond, but they don't show it in this diagram. So here's the double bond here, that's worth 500. So we're going to break that, bam, break it, and that thing is worth 500. And so these are the bonds that are broken. If we put all these right here, boom, that is what, 1380. 1380, if I did my math right, minus, let's figure out how much energy is involved in the bonds that are formed. 2 H2Os. So this is an H2O. There's an oxygen atom, a hydrogen atom, and another hydrogen atom. So we're going to build a bond right there. We're going to build a bond right there, and build there, here, and here. So 1, 2, 3, 4. Each one of those is an OH bond. Let's look. 460. So this one is 460. This one's 460, 460, and 460. So let me grab my calculator. Times 460, which is 1840. So those are the bonds that are formed. 1840. So 1380 minus 1840. Let's run that. 1380 minus 1840. 1840. Boom. So we end up with negative 460 equals negative 460. And that is kJ, kilojoules per mole. Okay, for this reaction to occur, actually this would be an exothermic reaction. It gives off, the negative sign means that it gives off 460 kilojoules of energy. So this reaction would feel hot. This is hydrogen bonding with oxygen to make water. And we're going to run this reaction in class as well in the lab. All right, and here's a couple more problems that you could try. So find the bond energy change. I'll just show you sort of how you would go about this, and then you can do the math. So remember, the equation is bonds broken minus bonds formed. So everything over on this side, these are the bonds that you have to break, and everything over here are the bonds that you're going to form. And let's see, so here's a molecule, C3H8, plus 5 O's, so you have to think 5 times whatever the bond energy is here. And then 3 CO2s, so 3 times whatever goes on right in here, plus 4 times whatever goes on here. So these are the bonds that you'll make. Bonds broken over on this side minus bonds formed. And so you're going to break this one, break that one, break that one, break that one. I'll just get you started. Break, break, break. I believe that is 8 carbon-hydrogen bonds, is it not? 1, 2, 3, 4, 5, 6, 7, 8. 8 carbon-hydrogen bonds. Carbon-hydrogen. There they are right there. 8 of them. 410. So you'd say 8 times 410, 340 or something like that. 3,000 400, I guess it would be. And 5 times let's see, where's that? There it is, 500 for those. So 5 times 500, I think that's 2,500. So you add all those numbers up. Oops, I forgot these. Carbon bonds. Shame on me. Carbon. Where are they? They're each with 350. So you add up everything on this side, and you subtract everything on this side. So C double bond O bonds. Let's look at that. C, there it is. C double bond O. All right. That bond is worth 805. That's a lot of energy. So is this one right there, 805 kilojoules per mole. And so you add those two together, and then you multiply it by 3 to get the amount of energy involved here. And then over on this side, you have an OH bond that's built. That's worth 460. This one's also worth 460. And you add those two together, and then you multiply by 4. And add everything together. And then you take what's on this side minus what's on that side. And that's how you deal with energy, my dears. A couple of other things that we just want to touch on a second right now. And those are some vocabulary words. For example, temperature. All right, what is temperature? It's a measurement of the kinetic energy or the movement of molecules. So when you wake up in the morning and you're wondering what you should wear, how cold is it outside, you should holler downstairs and say, hey mom or hey dad, how fast are the molecules moving outside? And they'll tell you, oh, it's the molecules are moving at 25 degrees this morning, or minus 13 degrees this morning. That's what temperature is. That's how fast molecules are moving. Next thing is heat. Now, heat and temperature seem the same, but they're definitely not. Heat is the energy transferred by a difference in temperature. And so we'll do a couple of labs regarding this. But the big idea is this: if you have a teacup filled with hot water and a bathtub filled with hot water, even if they're the same temperature, the bathtub has a lot more heat. There's a lot more heat in there. Next vocabulary word is specific heat, and that's the heat required to raise the temperature of 1 gram of a substance by 1 degree Celsius. Some things heat up and cool down very quickly, and some things are pretty slow. The next term is calorie with a little c, and that's the amount of heat required to raise the temperature of 1 gram of water by 1 degree Celsius. And then calorie with a capital C. So this is what you'll find on your Doritos packages. And those are actually kilocalories, or 1,000 calories. And we're going to do a lab with this as well. So one thing you want to start thinking about is this. We're going to run one lab that requires, we're going to have a setup kind of like this up here. We'll take some food and we'll heat it, we'll burn it, and give that energy to some water, and watch the temperature go up and figure out how much energy is involved in that reaction. So please bring a food item that burns easily, sticks on a pin right here, and it shouldn't melt, and also something that doesn't cause allergic reactions, like nuts. They are so full of energy, but we better keep away from those. Okay, well, I hope you had a good lesson today.